Hello everyone, and welcome to part 2 of plate tectonics. Last time we talked about how a volcano, can I move the slide? Let's try. A volcano in Iceland caused the French Revolution, which it didn't really, but it kind of did too. So yeah, but we want to move on, and that's a divergent boundary, right? And we want to move on and talk a little bit about how these things develop. A lot of times these divergent boundaries will come up underneath continental crust, and so you get a kind of a sequence of events here, if you will, where as that magma comes up, you'll get upwelling as the crust is kind of pushed upward, and then eventually you'll get actual motion and rifting, which will make a valley. And then eventually that valley will flood into a linear sea, and then eventually it becomes an ocean basin. Now we have a really good example of this second part, this part B, if you will, here, of this process over in Africa. In Eastern Africa. The Horn of Africa, if you will, what would geopolitically be, I guess, Kenya, probably Somalia, I believe Uganda. I don't know my African geography that well, but this part of Africa here is moving to the east, where the rest of it is kind of moving off to the west. And so this is that rifting phase, right? This is that phase kind of right here, where the continent is breaking apart, making what we call the Great Rift Valley. Down through the center of Africa. Now, actually, it's a little bit more than that, because the Red Sea here and the Gulf of Aden, these three things, the Rift Valley, the Red Sea, and the Gulf of Aden, are all forming what we call a triple junction. For reasons that are not entirely clear, whenever the Earth breaks apart, or the crust of the Earth breaks apart, it tends to break apart in groups of three. And so, in this particular case, you've got the Arabian Peninsula. I can show you here, maybe better. I've got the Arabian Peninsula here kind of moving this way to the northeast, and that's opening up the Red Sea and the Gulf of Aden, and then also the Great Rift Valley of Africa running down through here. And here's what it looks like. And the right hand side is moving to the right, the left hand side is moving to the left. I'm not honestly sure what direction we're moving in here, or what direction we're looking, so I don't know. But you do know, if that's the axis of the valley, the right hand is moving to the right, the left side is moving to the left, and that's throwing up a whole bunch of volcanoes. Let me get out of here, and let me get into Google Earth, and if I run this over here, and I zoom in here, we can see the Rift Valley running down through here, kind of around Lake Victoria. And let me see, do I have my earthquake layers? I've opened a weird version of Google Earth. Hold on, let me pause this. I'll be right back. Okay, there's all my stuff. And so yeah, if I kick in volcanoes, and what that's going to do is add a layer of volcanoes to Google Earth here. Sometimes it takes it a minute. Sometimes there we go. And so we can see that generally we have scattered volcanoes, especially in the Sahara. But if we come down here, we see a remarkable accumulation of volcanoes running right down that rift, and actually around Lake Victoria. And so, these are happening because, once again, this side of the crust is moving this way, this side of the crust is moving that way, that way. And so in between, you've got, magma being drawn up, or rather mantle being drawn up, decompression melting and turning into magma and making volcanoes. Now, of course, included in these volcanoes, let me go back to the PowerPoint. Here we go. And I'll put it all in that little window so you all can see everything. There we go. And so included in those volcanoes is Mount Kilimanjaro, which is the tallest freestanding mountain in the world. In other words, it's not like, Everest, it's part of a mountain range. It is one volcanic mountain sticking up above the Kalahari, and it is the tallest, like I said, freestanding mountain in the world. The other interesting thing about about this area, though, is this is where humanity comes from, right? This Rift Valley is where we got the first, what we would call AMH, anatomically modern humans, right? Someone you, oh, look, a person, right? And even before they were anatomically modern, they migrated out of this area into Europe and then down, of course, into Australia and all over the world across the Bering Straits, down into North America. And these dates are hinky. And by hinky, I mean not exact. In fact, I know that we place human occupation in Florida now at about 16,000 years ago. So those dates definitely have some wiggle room. But yeah, so you can see, how we spread. But we begin here. This part of Eastern Africa is where we find the fossils of our human ancestors and our first humans. So it really is a remarkable place. So that's divergent boundaries, right? Triple junctions, Iceland. Where's Iceland on here? Oh, Iceland isn't even on here. So it's like there. So anyway, triple junctions, mid-ocean ridges, right? All of these things are divergent plate boundaries. Now, we also, though, what happens if two tectonic plates are coming together? Well, we call those convergent plate boundaries. And in order to get this, we need to understand that there are two different kinds of crust. There is continental crust, and then there is also oceanic crust. And these are different. And this is why, by the way, the oceans are where they are and the continents are where they are, because the oceans are underlain by fundamentally different crust. And in fact, if I go on to the next slide for just a second, I really like this map. It's just kind of fun. But this is a contour map of the thickness of the crust. So whether you exactly know what a contour map is, the numbers correspond with the thickness of the crust. And you can see that oceanic crust is pretty much consistently 10 kilometers thick. It just kind of is. On the other hand, continental crust, kind of normal, generic continental crust, if there's nothing going on, is about 40 kilometers thick. On the other hand, it could be thicker. For example, 70 kilometers thick underneath the Himalayan mountains, 60 kilometers thick underneath the Andes Mountains, but only 30 kilometers thick in the Basin and Range area, where we've had some extension going on. Let me get a drink of water. I'm going to catch in my throat here. So we have two different kinds of crust, and this shows it very distinctly. And this shows one aspect of it, that continental crust is thicker. Oceanic crust is definitely thinner. Continental crust is less dense. I say light, okay. Less dense is probably a better word, because it's made of granite. And by granite, I don't literally mean granite. I mean, most of you live in Florida. That's limestone, okay? But generally, silica-rich rock. If we took all the rock on the continent and we melted it down, put it in a giant hopper, melted it, and let it cool, it would come out being something like granite, which is relatively less dense than basalt. Oceanic crust is only about 10 kilometers thick. It is relatively dense, a little bit more dense than that continental crust is, and that's going to mean something to us before too long. And so if I have two different kinds of crust, if I've got thick, lighter continental crust, and I've got thin, denser oceanic crust, that brings up three different combinations, right? So if I'm going to bring these together, I can bring ocean up against continent, I can bring oceanic crust up against oceanic crust, or I can bring continent up against continent, right? Each of those is a little different. They produce a little bit different tectonic setting, right? And so we can see them, the three of them pictured here, where you have, oceanic crust meeting continental crust, oceanic crust meeting oceanic crust, and then continent meeting continent. Okay, so let's take a look at the three, each of these. Like I said, they're each a little bit different. So if I bring oceanic crust up against continental crust, right? So what's going to happen here is you've got oceanic crust that is a little bit thinner and a little bit more dense. It meets continental crust which is a little bit thicker, a little bit less dense. Okay, so that oceanic crust is going to go under that continental crust. That process is called subduction. It might get shoved up here a little bit, but that's not going to last. Eventually, it's going to break off and it's going to go underneath there. Okay, so as it goes down, it grinds, right? And you start to get earthquakes. You get earthquakes right in here, in this area right in here, right? That area is called the Wadati-Benioff zone. When I first learned it, it was the Benioff zone. Then it was the Benioff-Wadati zone. Now it's the Wadati-Benioff zone. Whatever. Okay, some combination of Wadati and Benioff. But this gives us an interesting pattern, because as you look at this, you can see that the earthquakes up here are going to be relatively shallow. And then as I move back into the mountains, away from the beach, those earthquakes are going to get deeper and deeper under my feet. Now you're still going to get some up in here, but generally you're going to get earthquakes deeper and deeper as we go down. And then eventually you'll run out of earthquakes. Because but that, yay, no more earthquakes. Maybe not, because the reason you're running out of earthquakes is because now the crust is melting. And as it melts, it rises, and you get volcanoes here on this back side. These are not the happy little Hawaiian, let's go roast a pig and have a luau. And no. These are nasty, runaway or die volcanoes. You do not want to be around when these volcanoes go off. Let's take a look at Google Earth again, though, and see where we can see this. So not here, this is different, okay? But let's go, if I can get Google Earth to cooperate with me. Hooray, it is. Okay, so look at the west coast of South America, right? You've got a plate out here, the Nazca plate, that's moving this way. It's getting shoved underneath a plate here, the South American plate, right? And we're getting that. So we're definitely getting these volcanoes from the subducting crust. The blue ones or green ones or whatever color that is are a little bit younger, by the way. But what about the earthquakes? Well, let me just for the sake of clarity, let me get rid of the volcanoes and kick in some earthquakes. And so give this a minute, and oh, good, it worked. So these are color coded by depth, right? And so here's a nice little swarm of them right here. And all these are within the last, I want to say, week or so. But here's a nice little swarm of relatively shallow earthquakes, right? Somewhere between 0 and 33 kilometers down. If I look here, here's a deeper one, 70 to 150. And then if I look back here, these blue ones are the furthest from the plate boundary, and they're the deepest. I can actually, if I click on that, it'll tell me that one is 210 kilometers down. Okay, so you get the deeper earthquakes back here, and the shallower earthquakes generally closer to the plate boundary. Now this one's maybe a little bit shallow for where it is, but that's okay. You get earthquakes in the upper part of the crust too. So it's not like a absolute positive thing, but it is a thing. And so this would be one of those things that we would know but not understand without plate tectonics, right? We would know that we tend to get earthquakes here, and we tend to get volcanoes here. We would know that the earthquakes got deeper as you went back from the shoreline, or from, in this case, the plate boundary, but we wouldn't know why. Understanding what's going on here, right? Understanding that you've got some crust out here getting shoved underneath here, and it's going down at an angle, etc., right? Knowing that explains why, which is what I meant when I said, plate tectonics gets, the things that we know about geology to make sense. Now, we don't need to go all the way down to South America to see this. And the earthquakes here aren't as well arranged as they are in South America. So let's get rid of that. But we can kick the volcanoes back in, and we can see our Cascade Range here forming as the Juan de Fuca. Let me see if I can get rid of the names. There we go. Forming as the Juan de Fuca plate out here, a little plate off the coast of the Pacific Northwest, off the coast of kind of Northern California, Washington, and Oregon, named after the Juan de Fuca Straits right there. As the Juan de Fuca plate out here gets pushed underneath North America, you have that same thing going on, right? You've got that same melting, earthquakes, rising magma, and then volcanoes all up and down through here. And so, like I said, we don't need to go as far away as South America to see an ocean continent convergent boundary. We've got one right here. Right here in the United States. Okay, let me go ahead and get back to the PowerPoint and make it so y'all can see everything. And there we go. Okay, so this is what's happening. Both, west coast of South America is a good example. Our Pacific Northwest also a good example, right? And so, like there's, for example, there's Mount Hood. This you can see it right there on the schematic, and there's a photograph of it, right? And a lot of the volcanoes out here look like this. They're big cone-shaped mountains. We'll talk about them more when we actually talk about volcanoes. And the Pacific Northwest is really just beautiful. I mean, if you ever get a chance to go out there, definitely go out there. You've got these temperate rainforests. Beautiful hiking. It's just rivers. The whole thing is just beautiful. But every now and then it does that, and you don't want to be around when it does that. That's Mount St. Helens. And when we talk about volcanoes, we'll talk more about Mount St. Helens. Andes Mountains, same way. Andes Mountains are absolutely beautiful. That's not even the best picture of them. I need to find a better picture, but they are beautiful. Charles Darwin, in his voyage on the Beagle, spent a lot of time in the Andes Mountains, mostly because he got seasick. He wanted off the boat. But no, he spent a lot of time in the Andes Mountains, loved them. But once again, every now and then they look like that, right? You get these incredibly violent volcanoes. You don't hear a lot about them because there's not a whole lot of people living around them, so they don't really pose much of a danger, mostly because they're kind of out in the middle of nowhere. But still, they can be profoundly violent eruptions, and that's not a Photoshop or anything. Volcanoes really do make lightning, and we'll talk about that. When we talk about volcanic hazards. That's definitely on the list. So now what if I bring together oceanic crust and another piece of oceanic crust, right? So if I do that, they're both about the same density, they're both about the same thickness, but one of them's going to be a wee bit more dense than the other one, just a little bit, and so it'll go under the other one. And at this point, you get very similar conditions to the ocean continent convergent boundary, except the volcanoes are, first of all, at sea, and second of all, usually not as violent. And when we talk about volcanoes, we'll talk about why it is that some volcanoes, like let's say Mount St. Helens, are so violent, and other ones, like choose your favorite Hawaiian volcano, are not. There's a good chemical reason for that. But anyway, so we'll have, subducting oceanic lithosphere or crust here. We know they don't mean the same things, but we can kind of use them interchangeably, although I probably shouldn't. But and then oceanic lithosphere up here, same thing. Volcanoes on the backside, earthquakes, shallow to deep. Those volcanoes being formed by that melting, right? And if we want to see this, there's a couple of places we can go. One of them is in the Pacific Ocean. You may know, or at least be familiar with this picture of the Marines raising the flag on the island of Iwo Jima, the mountain named Mount Suribachi, during a battle during World War II. Here's what that island actually looks like. That's that mountain, which of course provided a place to shell the entire island and defend it. So they really truly didn't need to take it. But let me go back to Google Earth and show you that whole area there, because all of that is an ocean convergent boundary. Right here we are, right? And so we can see, there are volcanic islands here that you couldn't even see without, if I take the volcanoes out, you don't even know there's islands there, but there are. And so, and once again, you've got the Philippine plate over here. You've got the Pacific plate over here. Relatively speaking, this is moving this way. Relatively speaking, that means this is moving this way. They're both oceanic. So this is going to get shoved underneath that. And bingo, all of these volcanic islands, which of course lead straight to the mainland of Japan, which is why they were strategic during World War II. But anyway, so yeah. And of course, now Japan is very tectonically complicated. There's a lot that goes on here. First of all, you can see there's a lot of volcanoes and whatnot. But but one volcano in particular. Let me go back. Oh, let me show you this before I go back to the PowerPoint. Let me show you another place where this is happening. You don't need to go as far as the Pacific, right? Let's just look at the Caribbean. You've got the North American plate here, actually. You've got the Caribbean plate here, which is actually a whole bunch of little plates, but we'll treat it as one for now. And then, so where this gets shoved underneath that, look, volcanoes, right, all up and down through here. So all these little islands in the Caribbean that everyone goes to hang out on, and I've been to a couple of them myself. They're volcanic. They are volcanic islands formed from the North American plate getting pushed underneath the Caribbean plate. And so let's jump back to the PowerPoint and do that and do this thing. There we are, and we can leave this behind. And there's Mount Fuji, right? Beautiful mountain in mainland Japan that is a result of this process, right? And like I said, Japan is tectonically very complicated, but you get the idea that you've got oceanic crust getting shoved under oceanic crust, earthquakes, shallow to deep, and then volcanoes kind of on that backside. Okay, so what if I smack together two pieces of continental crust? Well, that's interesting. They're both relatively light and they're both thick, and so neither is going to go down into the mantle of the Earth. So they're just going to hit and thicken, right? And so since things are hitting and grinding, excuse me, you're going to get a lot of earthquakes. But you're not going to get any volcanoes. Nothing is going down right into the mantle and melting and rising and coming back up. Okay, so when you think of this, think of your favorite mountain range that isn't volcanic, right? Odds are this is how they formed, and that heat and pressure makes a lot of metamorphic rock. Now, the poster child for this is the Himalayan mountains, right? And so you can see India here lurking offshore, not really lurking, actually moving northward, offshore and moving northward. So you've got, right now, and this is about 50 million years ago. Okay, so now in southern Eurasia, what will eventually be like Pakistan. Okay, you've got an ocean continent boundary, right? You've got oceanic crust going down, melting, rising, volcanoes. You got an ocean continent boundary, like the west coast of South America, Pacific Northwest of North America today, right? But India is out there, and India is moving northward, right? And then, bam, it smacks into Eurasia, throws up the Himalayan mountains, and is still moving northward. This is not something that happened in the past. India is still moving northward at about 5 centimeters per year. India is moving north about the same speed North America is moving to the southwest. And so that throws up a very tall and very young mountain range. And I'm going to pause this again just to show you, so I can get something set up to show you guys. I'll be back in just a second. Okay, I'm back. So this is a fun website. This is a reconstruction of the ancient Earth based on some work done by a guy named Chris Cotees. And the fun thing about this is you can drop a pin on your house and you can kind of follow your house through time. But what I want to show you right now is this. So this is Pangea. So obviously, we've got all the continents kind of in one large supercontinent. It's about 240 million years ago, and so if we look here, you can see the Appalachians here that we'll talk about more here in just one second. But what I want to draw your attention to right now is India, which is right down here. riding along with Antarctica, well, it'll eventually be Antarctica and Africa, and riding along. So what I'm going to do is I'm going to just kind of go forward through time. So 220 million years ago, India is pretty content to just kind of hang about here, down there, right there. And so if I go forward, it's just kind of noodling around. It even moves a little bit to the south. There it is right there, 150 million years ago. And then 120 million years ago, and then it decides, you know what, I'm going north. And suddenly it just starts absolutely tearing its way northward and then smacks into what will eventually be Europe and Asia. We just call the continent Eurasia. And so, but it's moving very, very quickly here. Most plates are moving, 5, centimeters per year. India's moving like 25 centimeters a year here. It's moving 5 or 6 times faster than any other tectonic plate. And it just goes up and smacks into Europe and Asia, continues to push northward, and is to this day still pushing northward, kind of burrowing its way underneath Eurasia. And if I bring up Google Earth, here we go, and let's go have a look at India real quick here. So there it is, and let me kick in earthquakes because that includes plate boundaries, and you can see these arrows here, pushing northward. IN is India, EU is Eurasia, and you can see it's still moving northward. They don't have numbers on here, but it's about 5 centimeters a year. So the Himalayan mountains are getting taller. Every year they get a few centimeters taller because once again, India hitting Eurasia is not something that happened, in the past. It's something that's happening right now. And you can see we're kicking off, a lot, we're kicking off earthquakes along here, sometimes big ones. You don't see a whole lot of volcanoes. There's one, a couple, but not really. And those are kind of don't actually count. So just bear with me on that one. But anyway, so this is a great example of a continent collision, but not by no means the only one, right? Just think about your favorite mountain range that's not volcanic, and let's go back in time. Sorry if I'm giving you seizures or something there, but our own Appalachian Mountains up here on the east coast of the United States, right? They formed when Pangea came together, right? And so the collision that formed Pangea would throw up those mountains. And you can see here's the east coast of the United States. Now this event is a little more complicated than just India smacking into Eurasia. There's several different times of mountain building in several different styles that make up the Appalachian orogeny or mountain building event. But here you can see, Florida and, the eastern part of the southern United States, riding along here. And then if I take this forward, bam, right? You can see here we tack Florida and the eastern United States onto what will eventually be North America. And for a while now, we've been throwing up, this mountain range that we today call the Appalachians. Like I said, this isn't quite as simple as we're just going to smack two things together. It's a bit more complicated than that. But you can see, how Pangea coming together, sutured together, Africa and North America, and threw up this East Coast mountain range. Made a very tall mountain range, by the way. The Appalachians were 300 million years ago a lot taller than the Himalayas are today. When you look at the Appalachian Mountains today, keep in mind that you are looking at the ground down nubs of a formerly much taller mountain range. The Appalachians that we see today have been eroding for 300 million years. That's a lot of erosion. Right now, as I record this lecture, I am right there in Charlotte, North Carolina, which would put me smack dab in the middle of the ancient Appalachians. Yet there's no mountains here, but there's a lot of high-grade metamorphic rock here. left over from that mountain building event. And so, and when you go up into the Appalachians today, that's what you see is very, very high grade metamorphic rock that is normally buried deep, deep in the roots of mountains. Completely exposed today, and that you don't if you go to the Himalayas, you see sedimentary rock on top of that. It's just been pushed upward and kind of out of the way. You don't see that in the Appalachians. It's all high-grade metamorphic rock. And when we talk about rocks, we'll talk a bit more about that. So anyway, so that's it. So once again, our Appalachian Mountains formed from a continent convergent boundary or convergent collision. What about the Rockies? Yeah, they're a lot more complicated. Let's not go there. The Rockies form from a series of small continent collisions, which is the easiest way to explain that. But they're a bit more complicated, so that's fine though. All right, so let's go back to PowerPoint and let's do this, and let's make it so y'all can see everything. And there we go, and there we go. Alrighty, so what if plates are sliding past each other? Right, so tectonic plates can do a few different things, or three different things basically. Right, they can move away from each other, they can move toward each other, or they can slide past each other. So we talked about moving away from each other. That's a divergent boundary. We talked about moving toward each other. There's three ways to do that. There's ocean-continent, ocean-ocean, or continent-continent. What if they slide past each other? Well, that's called a transform boundary. And so there is a couple of different ways to set this up. Okay, and one of them is at a divergent boundary. Now, as you look at this, the publisher made a mistake. See these black arrows? They're going in the wrong direction. I told them about this, and I'm hoping they fixed it in later editions of the book. But the one that I have right now, or when I made this slide, those arrows, those two black arrows right there, are going in the wrong direction. They should be going in the same direction as these as the white arrows are. But I tell you, let me show you how you can turn a divergent boundary into a transform boundary. And this is easiest really to draw. And this happens on the seafloor. I can show you where this happens on the seafloor. But if I have let's see. If I have a divergent boundary and I'm not... Oh, look at that. I switched the slide. I don't want to switch the slide. I want to draw something. Hold on. There we go. Oh, it would help if I selected the little drawing tool. Sorry, everyone. Kind of new to this. Still figuring it out. And pin. Okay, there we go. Okay, so if I have a divergent boundary here, right? And so we're looking at it from above. So this, this tectonic plate is moving this way, and this tectonic plate is moving that way. Forgive my horrible arrows, but I've got a tectonic plate over here A, and I've got a tectonic plate over here B. Now I can show you where this happens on the seafloor, and I will. But these divergent boundaries, they kind of stop and they offset. So let's say that this one picks up again over here, okay? And so now I've got, once again, it's a divergent boundary. So this side is moving that way. I really need to learn to draw arrows, but that's okay. This side is moving that way. And once again, this is still, this is still a tectonic plate over here, A. This is still a tectonic plate over here, B. Okay, but look at what's going on right in through here. Look at what's going on right here, kind of in between. Pretend it's a line. Actually, it doesn't even need to be a line. But anyway, look at what's going on right there. Now, this is a plate boundary, right? Look. Right, this is plate A right here. And right, this is plate B right here, right? So that line that I drew in there is a plate boundary, and apparently I need to draw lowercase letters because those are much better. But look at the direction that the plates are moving, right? This is moving this way along that line, and this is moving this way, right? And so I've got rock moving this way, I've got rock moving that way. I wish I could switch colors, but that's okay. And so what ends up happening is right in here, you have rock grinding, right? And whenever you have rock grinding, that is a recipe for earthquakes, right? So you're going to get right in there, right there, right along that plate boundary, you're going to get earthquakes. H-G-U-A. Pretend you can read my handwriting. Earthquakes. Okay. And once again, the reason you're getting those is because this rock here is getting shoved this way. This rock here is getting shoved that way. And so right there at that AB plate boundary, you're going to get grinding and you're going to get earthquakes. Now, what you're not going to get is volcanoes, right? Now you'll get volcanoes here. I can draw our little triangles that we're kind of used to for volcanoes, right? You're going to get volcanoes there, along those divergent boundaries, but you're not going to get them in here, right? There's no magma being brought up. There's no rock being shoved down to make magma. There's nothing like that, right? And so that's one way to make a transform boundary, right? Just offset two divergent boundaries, and you'll get a transform boundary. Here's the fancier. Let me get my pen off of there. Otherwise, it acts like a mouse. There's the fancier picture, and I fixed the arrows, my lame little way there, but there's the fancier three-dimensional picture. But you can see how you got the yellow plate over here. Sorry, let me just turn my pen off. There we go. You've got the yellow plate over here, and you've got the gray plate over here. And so where that transform boundary gets offset, in this case down here it's offset the way I drew it. Up here it's offset in a different direction. It doesn't really matter. But so you can see that as this gets offset right here in between, right? Let me draw again. What the heck? No, not laser pointer. I'm gonna draw right here, right in there is that transform plate boundary. And here's another one up here, right there in between those two offset divergent plate boundaries. And so if you want to see where this actually happens, let's go up here, right? Look right here. Apparently I'm all into the drawing today. Okay, fine. So look up here, right here south of Iceland, where you've got this divergent boundary coming down, and then it stops and it's offset over here, right? I can zoom in on it a little bit. There we go. Let me get rid. Oh, never mind. I don't need to get rid of it. But anyway, you can see comes down, is offset, and over here, right? And so once again, this plate's moving that way, this plate's moving that way, and so right in there, you're going to get a transform plate boundary. Now the one that everyone knows about, and it's honestly not the best example of it in the world, but it's the one everyone knows about, and that's the San Andreas Fault over here on the west coast of the United States, right? And so you can see you've got the East Pacific Rise coming up here, and then up into the Gulf of California here between Baja and mainland Mexico, and then it kind of turns sideways and it comes out again up here along the Juan de Fuca plate. You can't really see it here, so let's look at a diagram of it. Right, here's that divergent boundary coming up into the Gulf of California, and then coming out again up here along the Mendocino Fault on the southern side of the Juan de Fuca plate. And so Baja and westernmost California is getting shoved to the north relative to the rest of the North American plate that is, relatively speaking, moving to the south. Okay, now it's actually moving to the west, but if we're just thinking about the San Andreas Fault here, what's happening is a couple things. But if we're just thinking about the San Andreas Fault, basically the coastline of California up to just a little bit north of San Francisco is moving northward, where the rest relative to the rest of North America. And so if you're in California and you're standing on the beach, you're not standing on the North American tectonic plate. At some point or another, you cross the San Andreas Fault, and now you're standing on the Pacific plate. And you're not going to break off into the ocean. It's not like that. You're just going to continue to slide northward, right? And so what that's going to do is that's going to kick in a whole bunch of earthquakes, right? Let me show you. So, oh, hold on. Oh, yeah, discard the ink annotation. I don't need that. But let me show you on Google Earth, and so let's leave off of India. Let me get rid of these because it moves a little bit better. So if we look at California. And so there we are. So once again, so here's the Gulf of California, and so that that divergent boundary is coming up in here, and then so let's kick in some earthquakes and see, look at that, right? So you can see the plate boundary, and then you can see all of these earthquakes. So look at it, just a lot, right? If I let me see, I'm pretty sure I can do this. Let me take out the plates. See, even if you didn't have the plate boundary, you could find the plate, right? You could find the San Andreas Fault, right? These earthquakes are all lined up right along it, right? If I put the plate back in, you can see the red line there with those earthquakes lined up right along it, right? You're getting that now. It's the other thing to keep in mind is this isn't as simple as the San Andreas Fault. Okay, there's a bunch of faults out there. There's a San Andreas Fault, there's a Hayward Fault, there's a Northridge Fault, right? You don't just break the Earth in two pieces. There's going to be lots of little faults, but they're all going to run kind of north, west, southeast. And I mean, because you can see earthquakes here. They're not on the San Andreas Fault, but notice that a couple of things. First of all, they're shallow. Right, they're very shallow. They're all, I mean, they are shallow. If I let me just click on that's actually two of them, but that's fine. Let's get one of them. That's 3-4 miles down, right? And they're all going to be like that. They're all just going to be. That one is 3 miles down, right? These are very shallow earthquakes. That one, they don't even know the depth on that one. They think that one's in the air. That's an instrumentation failure. And so, north, I don't even know what that is. All right. Get off of there. And so, but here's one that is 5.5 miles down, right? So they're very shallow, and they're not very big, right? The bigger the circle, the larger the earthquake. No one felt any of these earthquakes. No one feels a magnitude 2.4 earthquake. They just don't. I don't care if they say they did. They didn't. Okay. All of these are little magnitude 2s, maybe a 3. You don't start feel. We'll talk about this when we talk about earthquakes, but you really don't start feeling an earthquake until it's a 4. Okay, no one really feels a 2 or a 3. They just don't. Okay, and so you can see. So this isn't like South America, right? We're not getting bigger, deeper earthquakes, right? It's a different tectonic setting, right? That's a 4.2. People would feel that. That's a 4.4, right? A 4.4, magnitude 4 and 5 earthquakes in downtown Los Angeles. You might hear about it on the news, and then also that's 163 miles down, right? Different tectonic setting, right? California is a transform boundary, right? So you get a lot of shallow earthquakes. You get a lot of shallow earthquakes, and they're not very big. There's an interesting little swarm of them going on there. None of them very big, but there's an interesting swarm of earthquakes, isn't it? That's kind of fun. And so I'll show you, when we do earthquakes, I'm going to show you the IRIS earthquake server, which is much better than Google Earth for investigating things like that. But let me kick in the volcanoes, and let's see what happens. So I kick in the volcanoes, and we get some out here, but we don't get any along the San Andreas Fault, right? Yeah, no, right? No, right? You're not going to get, right? You're not bringing magma to the surface of the Earth here at all. Okay, you're just not. So you're going to get lots of shallow focus, small earthquakes, but no volcanoes, right? These volcanoes out here, are unrelated to this plate boundary here across the Central Valley. So okay, I'm gonna let's take a break. So I've got 5 minutes of the grist mill at Stone Mountain. I was out at Stone Mountain this last weekend. Got us a nice calming film of that. So let's take 5 minutes. I'll come back and we'll wrap up Plate Tectonics. Now y'all take the break. Don't fast forward to it. I know you're going to fast forward to it, but take the break. Okay, get up, walk around, breathe a little bit, stretch a little bit, get yourself some water, and I'll be back in 5 minutes. Okay, welcome back. Wasn't that nice? That's one of my favorite spots. So anyway, that might one of my favorite spots that y'all just fast forwarded through. Okay, so anyway, if we add a bit more to this, we can see that in this part of North America, we've got two different um, tectonic settings, right? We've got the San Andreas Fault here representing a transform boundary. We've got the Juan de Fuca plate getting shoved underneath North America, making the Cascadia subduction zone an ocean continent, convergent plate boundary. And then, if we even look here on the western side of the Juan de Fuca plate, we can see some smaller transform boundaries. So we got a lot going on there. And if you look carefully in California, you can see the San Andreas Fault cutting across it, right? It's not at all difficult to find the San Andreas Fault. And in fact, if you look carefully all over, especially Southern California, you'll see all kinds of faults there. This is a block diagram from the Loma Prieta earthquake that happened back in 1989. I had just gotten out of the Marine Corps. But I like it, not necessarily for the Loma Prieta, but that it's a really nice block diagram showing what happened or what's generally going on out there, right? You've got the Pacific Plate here, which is westernmost California, the beaches, and a few miles inland, moving northward, right, relative to the rest of North America, which is relatively speaking moving southward. And sure enough, this kicked off a magnitude 7.1 earthquake about 11 miles down on October 17th, 1989. And when we talk about earthquakes, we'll talk about the Loma Prieta earthquake. But right now, what I want you to concentrate on is this nice three-dimensional view of this tectonic setting. And you can also see, like, there's the Hayward Fault, there's the Calaveras Fault, there's a Northridge Fault. There's all kinds of faults out there. It's not just one San Andreas Fault, but we can see the San Andreas Fault. Here it is. You can see, the fault running right across here like this. We're looking to the east, and so this is the Pacific Plate here moving this way. This is the North American Plate, relatively speaking, moving this way. And you can see how, it's moving at a scale, or at a speed even, that it's offset this river, right? This river, kind of should just be kind of going down here, but it's not. It's over here. This is the Wallace Creek area, which I think every geologist in North America has visited this particular location. But it's a really striking example of what these transform faults look like, right? With these these offsets, right? There's that creek coming down, ends up over here, right? If this wasn't moving, it would just come down out onto this plane. So there's our plate boundaries. Now, we talked about Alfred Wegener and how he put that idea of continental drift out there, and it didn't really fly all that well at all. And so we want to kind of step back a little bit here and make sure that we understand that there is a lot of evidence for this, a lot of evidence, right? And maybe the most direct evidence is, we can set GPS transponders into concrete now, leave them out for a year, and measure the plate motion. We can pretty directly measure the plate motion, but also there's some other things too that are kind of interesting. They're not, doesn't need to be fancy or complicated. Okay, maybe a little bit fancy, but not complicated. For example, we spend a lot of time drilling the seafloor. This is maybe not something that a lot of people know about, but we do. Both into the sediment and into the rock underlying the sediment. This is I believe, Japanese drilling ship. We have a drilling ship too. There it is, the Joy Resolution. I worked on this ship a little bit. It's headquartered out of Texas A&M, where I went to graduate school. Spent a lot of time. We'll talk more about ocean drilling I don't know. I'll find a way to work it in, but it's a fascinating thing. It really is. A lot of what we know about the ocean, a lot of what we know about paleontology and plate tectonics and all kinds of things comes from drilling, from drilling the seafloor, and not just drilling the rock, but also drilling the sediment. And when you do that, you see a very particular pattern where the sediments on top of the seafloor, and we'll talk about these sediments, get thicker as you move away from these mid-ocean ridges, right? And so up here, where the rock is younger, it hasn't had as much time for sediment to fall on it, and so you get relatively thin layers of sediment. As you move this way, though, that rock has been, down there for longer and has had more time for sediment to accumulate. And so out here, you get thicker layers of sediment. If you're drilling right on that ridge, you're probably not even hitting any sediment. You're probably going straight into rock. Absolutely straight into rock. If you're drilling out here, you're going to drill through a couple 100 feet of sediment before you hit rock. And so as you work your way back this way, it gets thinner. The other thing is just, and I'll show you another slide on this, but as long as I have this one up, the age of the seafloor, right? If you're up in here, that seafloor is very young. 0 million years old, or very young. As you work your way this way, though, that seafloor gets older and older, and it's igneous rock, so we can radiometrically date it pretty easily, and we have. And I'll show you a better slide about this particular thing here in a little bit, but most definitely, the age of the seafloor supports the idea of plate tectonics. The fact that you have younger rock here and older rock out here means that the rock is, coming up and cooling and moving this way, and coming up and cooling and moving that way. And so younger seafloor out here, older seafloor out here supports the idea that it's moving. Thinner sediment up here, thicker sediment out here also supports the idea that it's moving. Another thing that we have are hotspots. A hotspot is a plume or a tube, if you will, of magma coming up underneath the crust of the earth. And so what it will do is it will burn through that crust and make a volcano. But then as that tectonic plate moves over that volcano, it'll get, that tectonic plate will move that volcano off of that hot spot, and then it will make another volcano. Okay, I'm going to pause the movie and set myself up with a blank thing here, because normally this is where I turn around on the dry erase board and show you all something. So give me 1 second to get a blank slide in here, and then I'm going to show you how this works. Okay, I'm back, and I figured out how to get black ink on my drawing pad. Hooray! Okay, so what's up with these hotspots? Okay, well, so let's think about this. Okay, sorry if there was a hiccup there. It's because I had to figure out how to get my drawing pin to work. So anyway, okay, so what's up with these hotspots? Okay, so let's say that we have, and there we go. Okay, fine. Weird, my pin's being weird. Sorry, guys. Okay, so let's say that we have a tectonic plate, and we're looking at it now from the side, right? So we're looking at, for example, the Pacific plate from the side. Okay, so what we're going to have is I'm going to try to be fancy here with colors. And so we're going to have a plume of magma coming up, right? It's just a tube of magma coming up. What it's going to do is it's going to burn through that crust, and then what you're going to get, let me switch back to black, what you're going to get is a volcano, right? And so here, up here above that plume, you'll have a volcano, and you'll have an active volcano, right? So volcano, okay? But here's the trick, right? The plate is moving, right? The plate's moving this way, let's say. Okay, so now I can't redraw all of this. So what I'm going to do is I'm going to redraw the plume, right? So relatively speaking, what will happen is the plume will move over here. So now the plume's over here, right? So I can't draw arrows. So this volcano shuts down, right? Because it no longer has a magma source. But that's okay, because what we're going to do is we're going to make a new volcano, a new active volcano here, right? This, that burns through, active volcano. Okay, but once again, tectonic plate continues to move to our right, right? So now that plume, once again, I can't redraw the whole plate. I'm lucky to be drawing what I am, so bear with me. Right, so now, relatively speaking, the plume is over here. Okay, so this volcanism here shuts down, right? Because, stop that. This volcanism here shuts down because there's no longer a magma source, right? And so we get a new volcano there. My volcanoes are black, so let's switch back to black. So we'll get a new volcano here. Right, and once again, it's active because you've got a magma source. Right, we'll do it one more time. Right, tectonic plate continues to move to the right, so that plume is now off here to the left. Let me get this right. So now the plume is over here. Do I have? Nope, I don't. Sorry, guys. Fancy new drawing pad works really well when I know what to do. Plume's over here, right? This volcano shuts down. And we get a new, there we go, we get a new volcano sitting right here, right? So you can see that what we get, right? My volcanoes are really lame. But you can see what we get, right? We get an active volcano here. This one's erupting now, right? But a string of dormant ones strung out behind it, right? And so if I think about this, this is the oldest volcano here, right? This is the first one I drew, and then this is the youngest one right here. Boy, my writing's awful. It's even worse on this. Anyway, this is the youngest one here, right? And so if I draw an arrow from the younger volcano or igneous rock to the older volcano or igneous rock, right? So if I draw an arrow from young to old, notice it's the same direction the plate's moving, right? And so you get a situation with these hot spots, especially the really long-lived ones, where you'll have a younger active volcano, obviously young, on one end of your island chain, and then a string of dormant ones all the way out, all the way out. And so maybe this one is like 0 million years old, right? Maybe this rock here is 2 million years old. Maybe this one is, I don't know, doesn't really matter, 3 million years old, and maybe this one is 5 million years old, right? Like I said, doesn't really matter. But you can radiometrically date these rocks. They're igneous rocks, so you can radiometrically date them, and you'll literally get an active erupting volcano and then a series of dormant ones out behind. Now that's a side view. If I take a map view, right, what I'm likely to get is a pretty big volcano here, and since we kind of have our little red triangles that we're used to seeing for active volcanoes, I'll go ahead and drop one on here, right? And so you got an active volcano there, and then strung out behind it, you'll get a string of dormant ones, right, that are a little bit smaller because they've been eroded. They've had time to be, that volcano's been getting eroded for 2 million years, right? This one's been getting eroded for 3 million years. This one's been eroded for maybe 5 million years, right? And so you'll get a string of volcanoes, but once again, this one's erupting now. So that's the young one. This one erupted 5 million years ago. So that's the older one. And once again, if I draw an arrow from the younger volcano to the older volcano, that tells me what direction the tectonic plate is moving, right? Which is a very valuable thing to know. Okay, so you know what direction the plate's moving. Now here's the other thing. Let me just show you one more trick. And if you're in lab, you'll probably be doing a bit of this, right? Let's say that this is a map. Okay, so to make it a map, we need a couple things. First of all, we need a north arrow. Right? So there we go. So that tells us that if north is up, it's usually up. It doesn't need to be, by the way. It wasn't always up, but it is now. So if north is up, then we know that this tectonic plate, is moving east, right? We know that direction is east. So we know it's moving east. Now here's the other thing, though. How fast? Right, well, if I have a scale bar, which is the other thing that we kind of need to make it a map, right? So if I have a scale bar down here, and let's say that we know that scale bar, and I'm really, as you know, making this up as I go along, okay? But let's say that scale bar there is 100 kilometers, right? Well, I know this volcano here is 5 million years old, right? Okay, and I know that when it was active, it was over here. Right, so I know that it took this island here 5 million years to go from here to here. Well, how far is that? Well, that's 100 kilometers, right? So I don't know, just eyeballing it. There's 100, there's 200, I don't know. There's about 300, there's about I don't know, maybe about 450 kilometers. Once again, eyeballing it, totally eyeballing it. But, 450 kilometers, right? Well, it went 450 kilometers in 5 million years, right? That's speed, right? I can do a wee bit of math and get it into centimeters per year, which is, what we usually measure these things in. But so these very long-lived hotspots are very handy things because they can tell us the direction. I'm clicking on something. I have no idea what. They can tell us the direction the tectonic plate is moving. Pretend I circled that. And then they can also tell us, I can go ahead and, make this like a speed, right? They can also tell us how fast the tectonic plate is moving. So these very long-lived hotspots are, really very handy things. And so where can I go to see one of these long-lived hotspots? Let's go to Hawaii. Right, and so you can see here, there's the Hawaiian Islands, and you can see. Let me just switch my color here to red so that we can see me writing, because I don't know, I feel like writing on this. So anyway, but we can see kind of what we saw before, right? And so here's the, sorry, my pad is moving around here. Hold on, there we go. So can I erase that stray mark? Let's get fancy. Ooh, I can. How cool. Okay, so, this is erupting now, right? In fact, a couple summers ago, this whole area right in through here, had a pretty substantial eruption. Okay, so this is the 0 million year old rock, and then Kauai up here is somewhere between 3.8 and 5.6, right? So I was kind of handy in my ages, my example, because this is about 5 million years old or so, right? So once again, if I draw an arrow from the younger rock to the older rock, that tells me what direction the plate's moving in, right? And so once again, north is still up here. I think we kind of know that, but and so that tells me that between 5 and million years ago and now, the Pacific plate was moving mostly northwest. Now it kind of curved. I mean, I drew a, you can kind of see what ended up happening. I drew a straight line, but it should actually go like this, right? So it's kind of been moving in a curve. In fact, the newest volcano, Loiki, is down here, almost due south of the Big Island. So there's been a little bit of a change in the direction that the Pacific plate has been moving over the last 5 million years. Between Oahu and Kauai, it was much more west than north. But you can see here between Maui and the Big Island, a little more north. So yeah, and so anyway, so you can get speed off of this too, right? If I know how far it is from Kauai to the Big Island, then I can do a little bit of division and get the speed, right? And so we can get direction and speed off of these long-lived hotspots. And the Hawaii hotspot is a very long-lived hotspot. On the other side of the Hawaii islands is the Emperor Seamount chain, these undersea volcanoes that go all the way up into the Aleutian Trench, right? And so and here's a fancy picture of what I drew, much better than what I just drew. But you can see how you've got a rising mantle plume causing, a an active volcano here on the right hand side. I'm going to go back to pointing, not drawing, because drawing kind of makes a mess of things. So you got an active volcano there, but then you got inactive volcanoes here, extinct volcanoes here that moved off of the hot spot, right? And so you can see their arrows showing plate motion. If I draw an arrow from the younger rock to the older rock, it shows me what direction the plate is moving. I mentioned the Emperor Seamount chain, and there it is. And so you can see here's the Hawaiian island chain here. But it is geologically part of this whole string of dormant underwater volcanoes that runs all the way up into the Aleutian Trench. The oldest seamount in this chain is 80 million years old. That hot spot right there has been there for 80 million years. That is amazing. That is well before the dinosaurs went extinct. And so, and then you can also see this dogleg right here, where the direction of the Pacific Plate changed pretty substantially. Here between 80 and 48, about 40 million years ago, the Pacific Plate was moving mostly due north, right? Let me go back to my drawing here. Sorry, I don't seem to be able to help myself. But if I go back here, if I draw an arrow now, and the key with drawing these arrows is it doesn't need to be zero. If I draw an arrow from the younger rock to the older rock, what was that? Don't do that. If I draw an arrow from the younger rock to the older rock, it just looks like that, right? It's just from 48 to 80. That's due north. Right? And then if I draw an arrow from the younger rock to the older rock, looks like that, right? And so that's kind of northwest, right? And so right here, about 40 million years ago, there was a pretty substantial change in the direction that the Pacific Plate was moving. It shifted from moving, almost due north here to now moving, more northwest here, right? And so that shift happened right about there. It happened about 40 million years ago, and we know that from the from this hotspot. Okay, so I am going to stop here because the next thing we want to do is some paleomagnetism, and I want to actually take a careful look at my PowerPoints because this is not difficult, but I want to make sure I do the best job explaining it that I can. So I'm going to go ahead and render and upload this for you, and I will get on with looking at this and making sure that I can explain this effectively. Okay, y'all take care. I'll see you again soon.